Hi, Nitty. Wow, Nitty, I hope you are feeling better. Wow, we hope to see you real soon. Okay, tell you what, we've got a new lesson on 15.5 day 1, a start of getting into some physics applications. And those of you who are taking advanced science classes, this is where multivariable calculus can really come into play. Density. Density is a measurement of units of mass per unit area. And over the next days, not necessarily consecutive days, but several other days here, we're going to consider a thin plate, also known as a lamina. And we've got this density function. By the way, this is the Greek letter rho. And, we've got rho as a function of x comma y. And rho is assigning a density for a point. So density is mass per unit area. So maybe as you're looking at this, if you're just paying attention to units, you can see with rho, if that would be mass per area, and then if dA itself would actually calculate that area, you can see as you work that out with your differentials, you would say, well, hey, if we are multiplying a density function to a little area subsection, that should accumulate mass. And that's exactly what we're doing. So density functions, you do a double integral and work that over that area, you find mass. Now, physicists also will use different types of density functions in a similar way. Rather than call it a density function, you could call it a charge density in electricity. So it would be a measurement of how many units of charge per unit area. In a very similar way as you integrate that, and here we could say, the Greek letter sigma. As we integrate sigma here, you'd actually find the total charge in a given region. So you can definitely see that, we can have some great applications. Let's deal with one of these electrical charge applications and say charge is distributed over a triangular region. We could call that, really thinking of that as a lamina. And we're going to say we're going from 0, 0 up to 0, 1. And we've got 1, 1. And, charges distributed over that triangular region with these vertices. In other words, connect those points, make your triangle, and there it is. Okay? And we're given sigma, a charge density right here. Remember, that's a charge per unit area. A charge per unit area. So if you'd plug in any xy coordinate right there, it would be that many charge units, which I believe are in coulombs, and they are, you can see they're right here, coulombs per square meter. So what we'd like to do is find the total charge. So in other words, we might expect to see different charge densities at different locations. Tell you what you might have to do here. You might have to just say, well, up on top, we've got the function y equals 1. Down below, this diagonal line, I think we could all agree, would be y equals x. It's the identity function, isn't it? And over here, we'd have the line x equals 0, should we need to use that. Well, just following this general guideline, we can say, well, if I want to find the total charge, which we could call Q, we're going to integrate with d here, and then we've got, sigma, which is xy, and we just have to integrate over that general region D. Now we're going back to saying, well, let's think about what type we'd like to have. Truly, we could think of this as a type 1 or a type 2 region. You have a choice, and when kids have a choice, 99% of the time, kids say, I'd like to think of this as a type 1, and myself included. I think I'd like to think of it that way as well. So, as you look at this, you can say, well, I've got x, y. That means type 1, I'm going to deal with y boundaries. Down below, it's bounded by y equals x. Up on top, it's bounded by y equals 1. And then I'm going to integrate for dx. We'd like to know all such vertical lines. They span from x equals 0 to x equals 1. And guys, this is just one such application problem, one in which you're now going to be able to find the total charge. We can work this out quickly. Even just taking an antiderivative with respect to y would get y squared all over 2. And using the fundamental theorem here, we can continue. We could say, well, we're going to integrate from 0 to 1. Plug in that 1. You can even say you've got x over 2 outside. You'd get 1 squared is just a 1. Plug in your x, you'd get x squared. You'd have that right there. And then you're virtually done. Just distribute that in. It's probably just as quick to work this thing out just by hand. Bump this up to the second power. Of course, then we're going to have to divide by a 2. We'd get x squared all over 4. Always can double check your antiderivative by taking the derivative to make sure that you've done that correctly. Take an antiderivative here. We'll bump that up to x to the 4th. Divide by 4, you'd get that 8. And a fundamental theorem, we just plug in a 1 and a 0. We've got 1/4 minus 1/8. And, of course, that's 2/8 minus 1/8. You get 1/8, and that would be a 1/8 Coulomb charge on that little plate, on that lamina. Okay? We doing all right? So you can see this is where, if we dealt with mass, instead of charge, it's pretty much the same concept. Now, I said earlier that there was another little learning target that we could squeeze in, and that's finding the moment of a particle. The moment of a particle about an axis is the product of its mass and its directed distance from an axis. So if we wanted to find the moment about the x-axis, you could say, well, we have to consider a point's distance from the x-axis. And here you can see a nice picture. Your x-axis, of course, is down here, and any point that's going to have a distance from it would be measured in a vertical distance. We really are measuring by the y-coordinate. So that moment is a product, a multiplication of the mass and its directed distance. Similarly, the moment of a lamina about the y-axis. Here's a y-axis. If you wanted to measure directed distance, you're measuring a horizontal distance. You'd really be saying, what is the x-coordinate? And that x-coordinate would measure the distance from that point in question to the y-axis. Now again, what we're going to jump into is we're going to say that the moment about that axis then is the product, the multiplication of its mass and its directed distance. So if we flip over to the second page, we're going to be able to see these definitions of the moment about an x-axis. The moment about the x-axis, and we saw that just a second ago, you'd say, well, you got to measure your distance with a y-coordinate. What you're seeing is that moment then really is throwing in each individual y-coordinate multiplied to that row density function. So as many kids will quickly point out, they'll say, well, that moment, writing that as m sub x, it's like the other variable gets thrown into the integral, to measure that distance. Similarly, the moment about the y-axis, and by the way, we've got that in the top portion right here. You want to measure your distance, you are measuring an x-coordinate. And you can see that's really what we're seeing right here. If we want to find the moment about the y-axis, we want to multiply that distance from the axis to the actual mass. So, that's how we can sneak that in. Now, the moments themselves are usually a means to an end. I'll tell you the truth, we do work out these moments, but what we're going to really want to do is follow up right here. We can use the moments to find the center of mass, and that can be a very helpful endeavor. I'm sure you can see how very often you'd like to be able to work out a center of mass in everyday problems. The center of mass, plain and simply, if you look at it from this way, it's going to be m sub y over m to find x bar here. X bar, if we look off to the side right here, maybe if I multiplied both of sides of the equation by m, what you can do is you could say, well, if I had my mass times the average distance from the y-axis, you would, more or less come up with this formula right here. You could see that you have your moment about that y-axis. That's your distance from the y-axis. And really, that's what you would hope to see. In a similar way, we could say, well, if we were looking at a moment about the x-axis, where you had y inside of that integral, you would say, well, I would hope that would be mass times the average distance from the x-axis. So what we're about to do here is really just plow through some problems. Notice maybe this is what kids will, definitely, take note of. When you're finding the x-coordinate of the center of mass, you're going to have to work with an integral involving x inside with that moment. It's actually the moment about the y-axis. And similarly, as you're finding the y-coordinate of the center of mass, you're going to be working with that moment about the x-axis, which is really working with that y there. So that's something that you can definitely hold on to. For both of these, you find the moment, that integral that we were just talking about, divided by m itself. And the mass itself is what we have started the whole lesson off on. So this next problem is going to take some time and effort. We're going to have to go through the mass, that integral that we just circled. We're going to have to find the moments for both of the axes, and then we're just going to use these formulas for x bar and y bar to find the center of mass. So, we don't have a great deal of time left in this video, but we can hopefully get started with this and at least get a good beginning. We've got a lamina with vertices at 0, 0, 1, 0, and also 0, 2. And, as you're looking at that, of course, forms a triangle. And, I think you can see immediately that we would like to get some equations to help us. Remembering that the very first thing you learned about lines was probably y equals mx plus b. You can see that your y-intercept is, in fact, a 2 here. Your slope, you're going to go down 2 steps, and you're going to go right 1. So you're going to say my slope is negative 2, and over here we're going to have a y-intercept of 2. And it doesn't take too long for you to be able to get that equation of that, diagonal of that hypotenuse of that triangle. But of course, as we're looking at this, we're going to say, let's just find our mass. Let's just find m. And, we're going to just have to work this out probably as a type 1 kind of an integral. We're about to run out of time. And we